So let's talk about what things we have going on. We're going to have a quiz next Friday. Okay, and then there'll be a homework due on Monday at 7 a.m. And then I have office hours today, 1:15 to 2:15. And then if you're working on the homework, you have questions or something, go ahead and send me an email. I can try to answer them by email. If that doesn't work, we can always look over the weekend, get together over Google Meet. So I'm happy to do that. Please seek out help if you need it. Questions on things we're doing in the class. Okay, so then let's go ahead. We're going to talk about a number of things with acids today. I want to highlight, there are three types of acids we're going to talk about today. So we're going to talk about strong acids, okay, and strong acids fully dissociate in water. Okay, and that makes when we're trying to figure out pH, when you add a strong acid to a solution, it's easy to figure out the pH, or easier, because you don't have to do an ice table for that. Okay, then we have weak acids. Okay, they mostly don't dissociate water. In other words, that hydrogen, the acidic hydrogen, the acidic proton, hydrogen proton, same thing that we were talking about, an acidic one, the H plus stays on the acid for the most part. Okay, and we're going to talk about polyprotic acids. And they have more than one proton that can dissociate. Okay, and these are going to be, they can be strong or weak acids, and they can be both. Okay, it could also just be a weak acid. I'm not aware of one that's a strong acid for both protons, one or more protons. We'll talk about that. Okay, but we're concerned with all of these sorts of things. What I want to do though is start with a strong acid. So when you want to figure out the pH of a strong acid solution, you just assume that that acid fully dissociates. So we're going to assume that it fully dissociates, and then we're just going to calculate the pH from the proton concentration, which is what we're going to do every time. I'm going to say proton here because then I don't need to do a subscript, okay, or a superscript. And so let's go ahead and somebody give me a strong acid. What's a strong acid? You have some acids you need to memorize. They're almost all strong acids. HCl, okay? Hydrochloric acid is the acid that's in your stomach. So what we can think about is, so we've got HCl, I think that's aqueous, and then it's gonna fully dissociate, but it's in equilibrium with H plus Cl minus. Okay, and that has a dissociation constant that's going to be something over 1, right? I think HCl, we saw it maybe the other day, it was 10 to the 6th, so it's a lot over 1. And these strong ones, that's what we're going to have for it. So then we could have a problem that said, what is the pH of a, let's go ahead with a 0.0032 molar solution of HCl. Okay? And so this is the solution. So you make a solution, you dumped enough HCl into water to get that concentration. For every one of these that dissociates, how many of these do I get? 1. And how many of these do I get? 1. So what that means is it all turns into these, right? But I get it one for one, so that's the concentration. That's this concentration for both of them. Okay. So what we can say is my H plus concentration is equal to my Cl minus concentration is equal to, in this case, 0.0032 molar. Questions? And then we would say our HCl concentration is 0. Okay, it's probably not. It's not 0. It's some tiny, 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 tiny number. Okay, but we're not gonna worry about it. We could actually use that equilibrium constant in reverse. The way we would do that, but we're not going to. But the way we would solve that is we assume. So let's say our Ka is 1 times 10 to the 6th. I would assume that all of this gets made, and then I would do the reverse reaction from equilibrium to figure out the tiny amount of HCl that is left. But we're not. That's the way to do it. We're not going to do those in here. Okay, so now I was asked what the pH was, though. So the pH is going to be equal to the negative log of the hydronium ion concentration, right? Which is equal to the negative log of 0.0032. And it's going to be something around pH 3 or 2 point something, 2 point something.
Do not say that for strong acids dissociating that it's not equilibrium. It's just because it goes forward.
That's a good point. We do write those as not equilibrium because it's so much that direction. You know, everything is in equilibrium, but sometimes you draw straight, do arrows, and sometimes not. It's field specific, but you're right. I talked about it in that manner. And so I get 2.49 is my pH. Okay? Other people get that? Questions on how we do those? Those are easy. Did you have a question? No? Okay. All right, so let's try a weak acid. How are we going to do the weak acid? Well, let's take hydrofluoric acid. Is one of the acids you need to know, right? This is the dangerous one that dissolves glass and goes through your skin and dissolves your bones, all sorts of fun stuff. But I'm going to go ahead and write this. I'm just writing the water in for fun, right? All these things, to show all these things are the same. Okay. And then H plus plus, oh, so H3O plus at this point because I put the water in, plus F minus. It's aqueous, that's aqueous, right? All right, so we've got that reaction, and the Ka for this, I think, is 6.3 times 10 to the fourth. I'll look at my notes. Yes. Okay. 6.3 times 10 to the negative fourth. And so the question here would be, actually I'll write the question up above so we can use the equation as written for our ice table. All right. What is the pH of a, let's call it a 0.23 molar solution of hydrofluoric acid? Okay? So what is that? So this is where we need to do an ice table. So what we've got is I'm going to go ahead and draw my ice table lines over here. We've got initial, we've got change, and we've got equilibrium. Okay? And so I'm going to assume that we start out with all hydrofluoric acid, right? And then we're going to start out with 0 of this and 0 of this. Okay. I'm not actually talking, we're going to start out with 55 molar water. All right. Because that's the concentration of water. I'm just going to leave it out, right? Because when we do our equilibrium expression, what happens to liquids? They go away, right? We don't worry about them. So we're just going to leave it out as we do this. But for so we start with hydrofluoric acid. Which way? All hydrofluoric acid and none of these. Which way does this reaction go? To the right or the left? To the right. It has to, because there's none of these. It can't go to the left. You can't have 2 of these come together to make hydrofluoric acid if there are none of them. Okay, so we have to do that. So I'm going to say that I have some of my HF go away. For every HF that splits up, how many H3Os do I get? 1. Okay, so I'm going to call it plus X. And then how many F minuses do I get? 1. So I'm going to do that as plus X. Now I'm going to write down my equilibrium amount. So I'm going to take this and add it to that, this and add it to that, and this and add it to that. And so I get 0.23 molar minus X is my equilibrium amount of HF. X is H3O, and X is, I'm doing 0 plus X. Yes? We're going to get to that. That's okay. So here we have a quadratic if we set this up, right? But this number is really small, and I'm going to give you a rule a little bit later. I'm going to give you a new rule that I see in your book. Your book's got a rule it wants to use. So we're going to use that rule for whether we can apply this. So far, we've been looking at it and saying that's very small, okay? But it really depends on how big is this compared to this. I've been careful the way I did this to make sure it works. And while I'm not going to make you do a quadratic in here, I think it's fair game for me to ask you whether you can do the simplifying assumption, right? Okay. We're going to always, when we work problems, it's going to be there, but I want you to know the test for it. But in this case, this is really small, and it's small compared to this is the important part. It's 400 times smaller or more is the rule that your book likes. So we're going to use that rule. And then, so I can not worry about that. All right. So now what we want to do is set up our equilibrium expression. So Ka is going to be equal to 6.3 times 10 to the negative 4th, right? And then go ahead and set up the equilibrium expression, the rest of the equilibrium expression here for it. I'll give you 30 seconds for that. Correct, correct. Yeah, but we'll do an example.
Okay.
And you may see different rules, different places. If I was to make up a rule, I'd make it 1,000 because it's a nice round number.
Isn't it just so that when you round it with safe things, like the answer is to be exact, like this?
Yeah. Okay, so hopefully what you've done here is we've got products over reactants, right? So my products are H3O plus and F minus, and my reactants are HF. And so I'm going to bring that down. Now that I've written enough of it out, I'm going to hope you, so remember, this is our HF. Actually, I'll write it underneath it. This is HF. This is H3O plus. This is F minus. Okay? And I'm just going to put the numbers in. So 6.3 times 10 to the negative 4. H3O plus is going to be X. F minus is going to be X. And on the bottom, we've made our simplifying assumption to get rid of that quadratic. That's going to be 23 or 0.23 molar. And now what I want to do is multiply both sides by 0.23 to get just x squared on one side. All right, these are going to cancel. And if I rewrite it, and I recommend when you do these, you show your work so you can get partial credit, but also showing your work and doing your work through each step will help you prevent making mistakes. I don't know if I said this in this class, I was having a horrible time making mistakes a couple days ago. And I was just forgetting stuff because I wasn't showing enough steps. And so 0.23 times 6.3. And so I get 0.00145. I'm going to go take the square root of that. And I get x equals 0.012 molar. Okay? And if we look up here, x is our H3O concentration and our F- concentration. So what I could do is just off to the right here say that's equal to my concentration of H3O plus. And it's also equal to my concentration of F-. My problem asked for what's the pH, right? So I don't need to solve for this, although that's my answer, right? I'm saying that it didn't change at all. I could actually subtract this out. And so then I'm just going to solve for the pH. The pH is equal to the negative log of, this is my H plus concentration, 0.012 molar. Oops, I had it in my calculator. And I get my pH, I get a pH of 1.92. Is that what other people got? If you had rounded a little bit differently, you might have gotten something slightly different, but something about there. Questions? So that's a weak acid, yes.
How can you take, like, do the pH equation for the concentration of H, like H3O? That's the
Okay, that's a good question. So H3O, we talk about H3O plus when this one in red. If I talk about H3O plus, that's the same as H plus. We're just giving the same names. And it's the same as if you hear me say protons, that's the same. They are all the same thing as far as we're concerned.
Okay, it's because it's like attached to water.
Yeah, a proton in water is not going to sit around by itself. It has to be associated. It's a super small positive charge, so it's going to stick to something. And so H3O plus is one model of what we say is going on. Let me go back and just show this picture from, I think, the last lecture, but maybe the one before that. There it is. Okay, so these are two models of how you could think about it. You could think about it as the H plus is here, and it's got a bunch of water sort of coordinated to it. Just think that is like hydrogen bonding. Or you could, put this cursor up here, or you could think about it as that it's stuck to one of those waters. And really what's going on is more complicated than either of these models. But it's a simple model that we use to think about it. But we'll use all of those interchangeably. Mostly I'm going to say H plus, or I'm going to say protons because it's easiest and it's the quickest shorthand. But when we go down, we're going to talk about how acid strength is related to the conjugate base strength later. And for that, we're going to have to use H3O plus. Okay, because otherwise the equations are going to be confusing. Other questions? Yes.
For the sig figs, you said the log has to be the number after the decimal, right?
Yes. So how many sig figs did I start out with? I started out with 2 sig figs.
But But the final answer has three sig figs, so is it just a number?
This is when you're looking at a log of something, talk about a pH. For correct sig figs, it's the number after the decimal point, so this is 2 sig figs.
Oh, so we don't.
Okay.
Okay.
But I want you to not, if you want to learn that, that is fantastic. But if you want to just ignore what I just said, and just, this would not have got, if you'd written it, I'm giving you 3 sig figs of sort of slack anyway, as long as you don't just give me one. Does that make sense? So, as long as you don't just give me 1 sig fig, or you give me, I'll give you 3 either side of whatever the correct number of sig figs is. So I just want you to be kind of close. Does that make sense? Okay, so that's the approximation. I don't want you obsessing over sig figs, but I will talk about what's the correct way to do them when I'm doing the problems. And the reason, one more, and then I'll stop. One more. The reason is that's your exponent. When you think about it, that's 10 to the first. So, right? Okay. So let's talk then about polyprotic acids. Got the set of rules I keep pushing down. We'll use these for our summary of what we've done in a minute. But so polyprotic acids. So polyprotic acids have more than one acidic proton. All right, so here I'm using proton for H plus or H3O, right? We're going to say proton for that. And when I say acidic, I mean one that can come off. All right, so if we were to draw methanol, which is not a very good acid, okay? But methanol is like this. This proton is acidic, meaning it can come off. That comes off at a really high, it's pH 15 it comes off, any reasonable amount. And then these are not acidic, they don't come off. Okay, you'll figure out in organic chemistry how to take things like that off, but it's really harsh conditions, okay? Not gen chem conditions, certainly not, I'm a biochemist, certainly not biochemical conditions. All right, so polyprotic acids have more than one proton, acidic proton, and the first one comes off easier than the later ones. Okay, and so if the first one comes off I'm going to say 100 times easier. We'll see how we calculate that. So we're going to be using Kas. Then we ignore all the later ones. Okay, essentially they're not making, you have very few protons come off for the later ones, and so we can just ignore it. It's gonna round out. We're gonna lose it in rounding at the end. So let's go ahead and use sulfuric acid for that. Okay, sulfuric acid is one of the acids you need to know and be able to name. This is the one that's in your car battery. Okay, so sulfuric acid has 2 protons that can come off. You've got the first one. Let's go make all this aqueous. And we get this. Okay, and then we have the second one can come off. So we have a second reaction where that second proton can also come off. Okay, The first one here, this is one of the acids, this is the acids in your car battery. It's one of the ones I have you memorize because you're going to see it at different times in your chemistry career, even if you don't have a long chemistry career. So this is one of those important strong acids that you may encounter in daily life as well. And so this first one, I'm going to say the Ka, and I'm going to write equals strong. It's bigger than 1. It's much bigger than 1. Okay? Sometimes really hard for people to measure these, but we just say that's strong. So that's going to fully dissociate. But we know it's bigger than 1. So our Ka for the second one, this is our first one, this is our second one, that's going to be 1.0 times 10 to the negative second. Okay? If this is 1 or greater, okay, so strong. So Ka1 we could say is greater than 1. And it's actually much, much greater than 1. I'm going to do that. Okay, much, much greater than 1. If it was 1, this is, you could put this in your calculator, this is 100 times smaller. So it fits our rule, right? 100 times smaller, and so we're just going to worry about this top one, and we're not going to worry about this. What it means is that we get almost all of our protons from this first dissociation, and we just get a tiny amount afterwards. Now, if you go on and take quantitative chemistry, you may learn the rules for actually, you can solve all of it. You can solve for exactly how much it'll dissociate using all of those, not using this assumption. But it's a later class sort of thing, okay? I don't know whether Dr. Keithley teaches that or not. All right, so let's go ahead and think about this then. Let's do a problem. So I'll say, what is the pH of a, let's go with a 0.18 molar solution of sulfuric acid. Okay, what's the pH of a 0.18 molar solution of sulfuric acid? So what we do here is we're just going to worry about the first dissociation. Now, if this was phosphoric acid, the first one probably also would be the only one we'd need to worry about, but it would be a weak acid and we'd have to do an ice table. Okay. Being it's a strong acid, we don't need to do an ice table here. So for every one of these that dissociates, how many of these do we get? 1. And how many of these do we get? 1. And so we can just say that it fully dissociates, so that's my concentration of each of these, right? We can do that for the strong acids. And then calculating our pH is easy. We're ignoring the second dissociation. And so the pH is equal to the negative log of this concentration, right? Because that is the concentration of my H+. Okay. So I can go and put that in my calculator. It's going to be something less than 1. And over time, hopefully get a little bit of a feel for where logs should land to just see whether you put something in your calculator wrong or not. That's something that'll come with a little bit of practice. I had 2 sig figs. That's my exponent. And then there I got 2 sig figs, so I got 0.74. Questions? Anybody else get it? Everybody else get that? Okay. So that's what we do with strong acids. So summarizing what we've talked about here, we have this set of rules. This is a figure from your book. And so if it's a strong acid, the amount of acid that's in there, it all becomes H+, right, for determining a pH. For a weak acid, we're going to have to ice table it, okay, regardless of what's going on. And then we've got an approximation here where the concentration of the acid added has to be 400 times bigger than the Ka for us to use that approximation, as opposed to doing the quadratic formula. Okay. And then finally, we have our polyprotic acids. And if that first equilibrium, if the first Ka is 100 times bigger than the next one, we can just pay attention to the first one. It's going to get like a 1% contribution, a small contribution that we can just ignore. Does that make sense? Okay, so then let's do a so I've removed having to do the quadratic formula or make this decision, but let's do a test. I could ask you about whether you needed to use it or not. Okay. So a solution contains, let's go ahead and use hydrofluoric acid. So let's go with 0.0543 molar hydrofluoric acid. Can you use the simplifying assumption with the in determining the pH? Okay, and I have to give you what the Ka is. We had it earlier. The Ka is equal to 1 times 10 to the negative 4th. Okay, you guys can go ahead and solve that while I go in here and actually do my subscripts and superscripts. Yes.
I was looking for the one we were talking about earlier, the one that we did with hydrofluoric acid earlier.
It was 6.3, wasn't it?
Yeah.
All right. Well, let's fix that.
Okay.
Okay, that's what it actually is. Sorry. It's not a tough calculation. Okay. So the way you look at this is here's how we're testing our approximation. There's my concentration. There's my Ka. So this goes here and this goes here, right? Okay. So I'm going to go ahead and I'm going to take 0.0543 and a molar. And I'm going to put 6.3 times 10 to the negative 4th underneath it. And if I put that in my calculator, I get 86. Okay. So can I use my simplifying assumption here? No. Okay, I cannot because it's not 400 or greater. So put a big red no. Oops. Try to put a big red no. No. Okay. All right, questions on that stuff before we move on? All right, then I want to talk about the relationship of the strength of an acid to its conjugate base. So the strength of an acid is related to the strength of its conjugate base. And let's actually say is inversely related. All right, we can see that down here in this figure. So what we have here is we have a series of acids. And so here you can see the really strong acids, right? Going through these, we haven't talked about perchloric acid. And at least last semester, I didn't have people in my class memorize the chlorates and chlorites. But the stronger the acids are, you can hopefully see that this is the conjugate base over here. The stronger the acid, the weaker the conjugate base. All right, this makes sense. If this is going to fully dissociate in solution, its conjugate base can't be picking protons out of water. It wouldn't be fully dissociated then. All right, so that shows us that they're related, and we can actually think about this and we can do math at it. If we think about hydrofluoric acid again, so hydrofluoric acid, when it is an acid, it's going to react with water, okay? And it's going to give us H3O+, and this is a place where I have to use the H3O+ thing, okay? Or else it gets confusing and we end up, if we can't, when we add up reactions, we end up with something different. And so that would be my acid reaction. That's my acid dissociation reaction. That has that Ka equals 6.3 times 10 to the negative fourth over here. If we think about the base dissociation of that, though, we think about what happens, not dissociation, but the base reaction. So what does this do? Well, if that's acting as a base, it's going to need to get a proton from somewhere. It's in water, so it's going to have to try and get it from water. And that's going to give me, this is F minus acting as a base. It's going to pull that proton off of water, and it's going to make OH minus. Okay? Are these reactions the reverse of each other? They're not. Okay? If I was to cancel everything out, it wouldn't cancel everything, essentially. All right, and the Ka here is equal to 1.6 times 10 to the negative 11th. Okay. So the important thing is that they're not exactly the reverse of each other. If they were exactly the reverse of each other, this, sorry, I wrote a Ka. That's going to actually a Kb because it's a base. But this would be 1 over that. Right? Remember, if we flip a reaction, we go 1 over that for the Ka. But we can't do it here because it's not the same reaction. However, there's an interesting relationship here between these reactions. Let's go ahead and add them together. Okay? If I add them together, I'm going to do this, I'll do it out. Let's do that. So I'm going to write HF plus H2O. That's my reactants for the top reaction, plus F minus plus H2O. That's the reactants for my bottom reaction. And then I'm going to, for my top reaction, I have H3O as a product for my top, F minus as a product for my top. I'm not going to do phases just yet because I'm going to cancel some things. Plus HF is a product on the bottom, plus OH minus is a product on the bottom. Okay. Do you see that I have an HF on this side and HF on that side? And I have an F minus on this side and F minus on that side? If I add these up now, I have 2H2O goes to H3O plus OH minus. Anybody recognize that reaction? That's the auto dissociation of water, right? And so we know that's equal to Kw. Kw is equal to 1.0 times 10 to the negative 14th, right? When I add two reactions together, what do I do with the equilibrium constants? If I add these two, I multiply these, right? Go ahead and multiply those. See what you get. 6.3. What'd you get? Yeah, you get this to two significant figures. Okay? So what does that tell us? Well, if I take, so what that this is Ka, this is Kb, right? That tells me that for a given acid, if I take the Ka for that acid, right? And then I take the Kb for its conjugate base, and I multiply them together, I'm going to get Kw. Okay? Questions? All right, let me show you something else. So we've talked about that. We've done a lot of things with negative logs so far, right? All right, so we've taken the negative log of a couple things. We're not done. There's actually a fun thing or a very useful thing in chemistry where we can take the negative log of the Ka, and that's equal to pKa, just like we have a pH, right? We have pOH. We can have a pKa. So that's the negative log of the Ka. These are big Ks, capital Ks. All right. We can also take that for the Kb. Okay. Why would we want to do that? Well, it's the same reason that we talk in pH. Because this is 6 point. What's the Ka for this reaction? If I want to describe that, the Ka is 6.3 times 10 to the negative 4, right? Okay, that's a lot of syllables. I'm going to get tired saying that all the time. So what I might say instead is the pKa is whatever that would be. Let's go ahead and take that. What's the negative log of 6.3 times 10 to the 4? 6.3 negative, okay, and I'm going to take the log of that, and I get, the pK is 3.2, okay? I would say instead, or 3.20, if I wanted to give better, correct significant figures there. Does that make sense? Why we would do that? Okay, so I can go up to this equation up here, and I can take the pKa of that, or I can take the negative log of that. So I can take this equation, and I can say the negative log of Ka times Kb is equal to, all right, if I have the log of something times something, what can I do with that? I can break it up and add them together, right? That's the same as saying the log of Ka plus the negative log, so the negative log of Ka plus the negative log of Kb, like that. Okay, that's a set of log rules, and that's equal to, well, I took the negative log of one side of the equation, I have to take the negative log of the other side of the equation, the negative log of Kw, like that. Okay. Remember, Kw is a constant, special for water, 1 times 10 to the negative 14th. If you put that into your calculator, that's the negative log of 1 times 10 to the negative 14th is 14, right? You can trust me, or you can put it into your calculator on that one. And then the negative log of Kb is pKb. And the negative log of Ka, because we just defined it as such, right? This is that, this is that, and so pKa. So my pKa plus my pKb is equal to 14. All right, just like my pH plus my pOH is equal to 14. All right, useful thing if you're trying to relate these really quickly. Now, I've got a little bit of time left here, actually more time. But I want to talk about what a useful bit about this pKa. So if we talk about pKa, right, that's something that we use a lot. I use it a lot in biochemistry. The pKa is, let me go ahead and type this, it's going to be a little bit long. The pKa is the pH at which an acid and its conjugate base are in equal concentrations. All right, so let's go back to this hydrofluoric acid example we've been using. So hydrofluoric acid can dissociate to make H plus F minus, like that. Okay. And we just calculated, right, the pKa for this reaction was 3.20. Okay. And so what that tells us is when the pH equals 3.20, the concentration of HF is equal to the concentration of F minus. Okay? These two things are equal. We're going to talk about buffers later, and that's really important in terms of buffers. A lot of you are in here probably because you're taking biology, right? Buffers are going to be important in there. So let's talk about one other thing. So we have this thing called Le Chatelier's principle, right? Le Chatelier's principle says, so this is at 3.2 at equilibrium. These are equal. This Le Chatelier's principle thing is so useful. Okay, it's so useful for looking at things and deciding things really quick. But before I use it up here, I need to remind you of something that you may not have quite yet, and it is confusing. And it's as the pH gets lower, what happens to the H plus concentration? Does the H plus concentration get higher or lower? Gets larger. Okay. So that's confusing because they're moving. We've got something that's talking about the H plus concentration, but when it goes down, the H plus concentration goes up. Low pH is a lot of acid, right? So that's something you're going to just need to get used to. It does drop out of the math of taking the negative log. Okay. All right. So what I want to say then, though, is when the pH is equal to this pKa, right? When these two things are equal, what happens if I make it more acidic? So I drop the pH. This goes up. Which way does my equilibrium shift? It's going to shift to the left. Okay. So what I can say then, something that's really useful, is I can say that if my pH is lower than the pKa, I have more of this than this. Okay? And vice versa. If the pH is higher than the pKa, I have more of this than that. Okay, where is that useful? Well, in biology and biochemistry, we're concerned with proteins. So if I do a protein as a big spiral like this, okay, in solution, it has some sort of shape, and it might have some acids on the outside, some things that look like this. All right, these guys have pKa's. Let's say the pKa of this equals, let's say, 4.0. Okay? What I now know is that when the pH is lower, so this thing right here can look like, if we think about what it looks like in solution, it's either in its acid form, right, or it's in its base form, like that, right? And so for whether this is in this shape or not, or whether it interacts with things or not, remember, we can explain most of chemistry using charges. It's important for me to know whether this is negative or this is neutral. And if the pH is above, so biological pH is what, roughly? 7, right? Your blood is 7.4, but it's things around 7. So if the pH is 7, that's higher than the pKa, and I know that I have mostly this form. Okay, important to know. That's where this pKa has become really useful.
And so, like, if you have an enzyme or something and say that's like on the like where it binds, the substrate binds, like, would that have to do with how well it functions?
Yeah, so in terms of enzymes, you care in the active site whether you have positive or negative charges, right? This can be neutral or negative, but we can get positive charges. And you also care what's going on the outside, whether the protein folds or not. This is why certain proteins work really well in your stomach and some don't at all. All right. You guys have a great weekend. And